Okay, now it's time to start the second session in the morning. I'm Professor Jinuk Lee. I will be organizing the second session. So our next speaker is Professor Alexander Yarin. Professor Yarin, thanks for coming today. So Professor Yarin is professor of Department of Electrical and Computer Engineering at University of Illinois at Chicago. He received his MS degree in Mechanical Engineering from Polytech Institute of Leningrad, a PhD degree in Physical Mathematical Science from Institute for Problems in Mechanics of USSR, Academy of Science, Moscow. He became a professor at Technion Israel Institute of Technology in 1990, and then he became a distinguished professor at University of Illinois at Chicago in 2006. So he published more than 390 research papers and received many awards, including Gottreich Award, Wholesale Reach Prize. So he actually sent us the video for his talk. He's gonna present about super hydrophobic PTFE, silicon dioxide electrospun fibrous membrane. To what extent are they really hydrophobic? So let's welcome Professor Alexander Yarin.
Good morning. This is a short talk you asked me to give about some material related type of works, which we do in the lab. And this is one of the latest related to development of special super hydrophobic Teflon-based membranes, which are presumably to be the best waterproofed material. Now here I'll also try to show you some science which is required, some like out-of-box thinking out of the material science, thinking to understand whether goals can be achieved, where poles can be achieved, and what happens, with super hydrophobicity in general. So therefore, we have here a question: to what extent they can really be super hydrophobic, these membranes? So let's go ahead. This is my work in collaboration with PhD students who worked in my lab, predominantly Fan Dongzhu, who was a visiting student from Donghua University, spent 1 year, Jen Lee, and my other PhD students and a collaborator from Donghua University. So please go ahead. Next one. Yeah, so a brief outline is like, the way how we form this material, the description of the resulting membranes, and then, some tests, which show to what extent they can be super hydrophobic and waterproof. And if I'll have enough time, I'll also briefly mention the breathability and durability and anti-fouling properties, which are also important for this material. So these materials are essentially developed not only to be super hydrophobic and water repellent, but also should possess some other properties. So several of them were tested in this work. Please go ahead. So the first is like the fabrication process. This is the emulsion electrospinning. So essentially I assume that you know electrospinning because Professor Senpilan is definitely an expert in electrospinning. So in brief, this is a process which allows you to make nanofibers, and in this case the starting material is suspension. So this is essentially like a suspension which incorporates a polymer solution, which is a polyethylene oxide solution, Teflon particles, and also glass particles, glass nanoparticles. So each component has its own role in this process. So after electrospinning, you essentially end up with fibers which incorporate all of these materials. So the skeleton of the fiber is predominantly polyethylene oxide. Now there is a lot of Teflon particles and also glass particles. Now the point is to make this material, first of all, super hydrophobic, and for that reason you need to remove the template material, which is PO. So this is done by sintering, so essentially heating and holding fibers for quite some time. So as a result of that, you remove PO and sinter Teflon particles. So then essentially it becomes, you know, Teflon and glass beads inside. So what's the reason for the glass beads? Because when you have sintering, so the material typically shrinks and can just before Teflon will be sintered, you know, it can be dramatically damaged and disfigured. So therefore, glass particles, which are absolutely solid during this process and do not shrink at all, they provide structural stability. So that's the final result, what you have, you know, as these membranes. So please go ahead. We discussed already this sintering process, and you see that with different Teflon PO compositions in the original fibers, the result of sintering might be very different. Here you see fibers, you know, covered with sinter fibers, you know, covered with a lot of PO, for example, which is not good, because when you expel PO from inside, you know, it accumulates outside. So then an appropriate combination of PO and Teflon should be found, and as a result of that, you'll make, you know, fibers which look like as shown here, or as the precursor membrane, which is shown here. So essentially, the best, you know, original membrane produces you the reasonable sintered membrane, and the main thing is that the structure of the membrane is the fibrous structure is preserved. So that is a membrane, and this is a porous membrane with interconnected pores. So please go ahead. These are the resulting membranes, you know, once again tested already in relation to the amount of glass beads inside. And you can see that the final results differ, and essentially, you know, like after sintering, you expect, you know, different porosity and different structure in general, different roughness, and this also should be more or less, you know, checked and decided what is the best composition. By the way, you know, these compositions are judged not only by the fibrous structure, but also then by like durability in abrasive tests and waterproofness in dripping test, as well as in self-cleaning. So therefore, essentially all these different compositions should be tested, and after all, that the trade-off should be found, and that would be the best composition. So please go ahead. Now, as I told you, fibers already shrink membranes, shrink during the sintering, and after all, you know, you should expect, you know, like a reduction in mass, and the content of a certain content of glass beads, you know, can reduce this sintering. So, for example, with more glass beads, you have shrinkage only by 10%. With less, you have up to 60%. So then you also expect, to find the fiber diameter. So the fiber diameter before sintering and after sintering is illustrated here. So we are talking about fibers of diameters about like a little bit submicron or micron size. So this I would call microfibers, not nanofibers. Now regarding the content of glass particles, you also see some tiny variation of porosity, so this is good. Essentially, it means that you keep, at all these glass bit contents, the general architecture of the membrane. Please go ahead. Then you also test water contact angle, so to what extent the membrane by itself is super hydrophobic, and you put softly a droplet on top of this membrane, different compositions obviously, and you see that the contact angle is always about like 150 to 160 degrees. So this droplet, looks up like the material under this droplet, water droplet, looks like absolutely super hydrophobic, which is essentially like considered, in this considered in this field as a good sign, and essentially in many cases it's considered to be the ultimate proof of super hydrophobicity. In the following, I'll show you that this is not the ultimate proof, and there are no materials essentially which can be super hydrophobic. Super hydrophobicity will be proven to be a conditional property. Okay, so roughness also varies. So you see the roughness illustrated here on the nanometer level. We also tested mechanical behavior because it's important, how robust is the membrane. So you measure stress strain curves. I don't have time to discuss this, but you can find, some details in the publication, the first publication we already put out with this. So please proceed further on. So the next thing is a water drop impact test. So essentially, like if you have a super water repellent material, you are interested, let's say if it's about closures, so you are interested first of all, how would it behave under impact of raindrops. So let's do exactly the raindrop type of experiment. So we'll put our membrane here, drip a droplet under gravity, and take a high-speed imaging to see what happens with water which comes to the membrane, which is presumably super hydrophobic. Okay, let's go ahead with this experiment. So the first experiment is, it's not with a membrane, but with a grid, just a metal grid which will be used, as a support for a very thin membrane. So you drip a droplet with a relatively low velocity of about 1 meter per second to the grid, and you see this is time development on the scale of milliseconds, and everything is good. The droplet, hits the grid, oscillates back and forth, and after all ends up on the outer side of the grid. This is a good sign for the grid, which does not even pretend to be super hydrophobic. Okay, it just protects. Okay, let's go ahead with the same grid. Okay, we'll increase the impact velocity. We'll just move droplets, the nozzle higher and higher. And you see that there is immediately several velocities where you can have droplet going through the grid. Okay, so the grid essentially does not protect from water, because water can cross the grid and drip like penetrate to the body if we are talking about clothes. So next slide, please. Now we are going with already our membrane. Okay, so this is not a grid, this is our membrane. And we drip a droplet at a relatively low velocity, and this is low essentially even in terms of raindrops. I'll mention the raindrops later on, but they go to 5 meters per second. Okay, so this is like 1 meter per second. Okay, and our membrane behaves perfectly. So the droplet hits the membrane, bounces off, and you see many different interesting phenomena, but after all nothing goes through the membrane. Now let's take a look what happens at a higher speed. Please go ahead. At the higher speed, you see that our membrane suddenly appears to be not super hydrophobic, okay, because water goes through, okay, so it doesn't protect. So there is a dramatic difference between the softly located droplet and a droplet dripping. So what's the reason for that? So this is not a waterproof membrane then. Please go ahead. The next one. Okay, so once again, you drip, at different velocities, different meshes, and different membranes, and you see that water droplets go through. So something is basically wrong with this membrane. So let's proceed further on. Okay, now let's restore waterproofness. So how do we want to restore waterproofness? Let's make membrane thicker and thicker. So the idea is, to make as thin as possible membrane to protect against water droplets. But you see that it's impossible to do. Then you have to go thicker and thicker. So to stop water already penetrating through viscous dissipation. That's the idea. Okay, so yes, and then you can, when you go to higher and higher thickness, for example, here there is a demonstration up to 11 micron thick membrane, so then you can prevent water from practically going through. Next slide, please. So here we demonstrate, the volume or fraction of water which goes through the membrane at different impact velocities. So see, the higher the impact velocity, the more water goes at a fixed thickness. So if you want to diminish this, you have to make a thicker membrane. Please go ahead. Now the reason for this failing waterproofness is in the so-called hydrodynamic focusing effect, which we once discovered. So essentially, it appears to be that when a water droplet, impacts at a pore of size d, and the droplet size is capital D. So then and it impacts with velocity v0. So then the penetration velocity is given by this u, and the ratio of capital D to small d might be on the scale, if the pores are small, might be on the scale of like 100 or even 1000. So it means that the kinetic energy which is coming with this big droplet, okay, is channeled into a very small pore. As a result of that, the penetration velocity is so high that whatever wettability related velocity which is shown here, predicted by the Lucas-Washburn formula, it doesn't matter. Okay, so therefore you can essentially deliver water into Teflon, any superhydrophobic material. That's exactly what happens. Please, the next slide. So this is the theory which we developed. It shows you where the pressure is during the moment of drop impact. So when the membrane is the opening is very small, like here and here, so you have very high pressure develops in this area. As a result of that, water goes into. This is a detailed hydrodynamic theory. I have to skip over this, and please go ahead. Now, is it possible to prove that what I'm telling you is true? Yes, that's a direct measurement we did, and you see here, some individual jets coming from the membrane pores, and we can measure velocity of these jets. And what is interesting that the measured velocity of this jet is higher than the impact velocity. So even so, you essentially, dissipate a lot of energy during flow in the pores. Still, the ejected velocity is higher than the injected velocity. That's exactly the result of the hydrodynamic focusing. Please go ahead. All right, this is superhydrophobicity once again. Please go ahead. Then you drip a droplet, which is I'll consider only this case of Teflon-based membrane. So you drip a droplet with kind of like nanoparticles, titanium dioxide particles inside. So then on the top you see this. Then go ahead. In the cut you see that, so which shows you essentially that water easily goes into this type of membrane. Please go ahead. That's what happens when the membrane is hydrophilic. I'll skip over this case where you definitely deliver intact. So then the critical thickness, you know, I told you that the membrane should be thicker and thicker and thicker, then to stop penetration, and we developed a theory which is essentially like accounting for the viscous dissipation inside the pores, and that's a prediction compared to the experimental results. So this is a prediction, this is the experimental results. At least, you know, like in the same range. This is a critical thickness. So you see that when you go from like 10 to about 50 micron thickness, you can prevent penetration up to about like 5 meters per second, which is of interest for water droplets. The next slide, please. So just in brief, you know, these membranes should also be not only impenetrable for water, but they should be penetrable for gas, breathable. So this is one of the experiments, you know, when hydrochloric acid evaporates, you know, through the membrane, and the marker, like a litmus paper, is located on top, and the marker changes color. So that's a manifestation of penetration of vapor through the membrane. In other cases here, water is in the pipe, the membrane is under, water is not going through this membrane, okay? However, gas is supplied here, and gas bubbles go through. So once again, penetrability, breathability is proven here. The next slide is the illustration. Okay, I'll skip this over because it's just a summary. Let's go to the next one. And the next one is anti-fouling and self-cleaning. So you can put, you know, different liquids, droplets on top of this membrane, okay, and you just tilt it and they roll over. Then you can put, you know, like carbon black, and using a small water jet, you immediately, you know, wash it away. Okay, so you can do this even with membranes degraded by a Brenner test, and still, you know, you're good and self-cleaning. So all in all, let me come to my conclusions. So the conclusions are shown here. The hydrodynamic focusing essentially can bring water through any membrane, superhydrophobic, not superhydrophobic, and the dynamic test like that should be done to prove, you know, that the membrane can withstand, you know, water droplets. This is number one. Now, if you have a thickness below a critical value, so the membrane fails. If you have a thickness higher than higher this critical value, so then only then the membrane would be waterproof. Now we show that essentially in the range up to 5 meters per second, what will guarantee waterproofness would be membranes in the range of from 11 to 56 micrometer, not less than that. Less than that, water droplets will go through the membrane. For comparison, I'm telling you that water drops can go up to 6 meters per second. Okay, therefore, to be sure that you have, you know, protection from water droplets during rain, for example. Okay, you have to have at least, you know, thickness of 11 to 56 micrometer, not less than that. And that's the end of my talk, and I believe I'm on time. Thank you.
Okay, thank you for a very nice talk, Professor Yarin. So Professor Yarin is online, so we can have the Q&A session. Is there any question from audience?
Don't be shy.
So I have some questions.
Yeah, please.
Okay.
Yeah. So I think your resulting fiber has a diameter of around 1 micrometer. Can you manipulate your fiber diameter by varying the size of your PTFE particles and glass particle size?
That's correct. Yes, you can use smaller particles, and then you'll have similar fibers, but smaller in diameter. Because after all, you know, what is left is just the skeleton of PTFE and glass particles. Yes, sure, you can make it smaller.
Okay, thank you. And And there was a stress strain curve, but you skipped the curve because of limited time. But I wonder the stretchability of your fiber, because I think the Teflon fiber can be used for maybe separator for lithium-ion battery or some other applications. So I think the stretchability is also could be one of the important factors.
Yeah, the fibers, you know, like the basic PO fiber is very stretchable because it becomes plastic and it's or hyperelastic and goes and goes. However, when you expel PO and you are left with only sinter particles, so then, you know, behavior, what I showed there is like that. Initially, you, as always, have elastic behavior. So then you have more or less like almost perfect plasticity. So the curve, you know, the stress strain curve tilts and goes not horizontally, but like with a relatively low slope. So essentially like almost like a perfect plasticity, but then it abruptly fails. So essentially you don't have, you know, that much stretchability as you had with the original peer, but still, you know, you have some degrees of freedom. And I can send you the publication which we put out already, so you'll see the exactly, you know, data there, which shows you to what extent you can stretch these membranes.
Yeah, thank you, sir. And the last question is actually about sintering. So, yeah. As you know, I did experiment in your lab regarding glass fiber for sintering. So, I also wonder about the change in mechanical property by you know, varying the temperature for sintering.
Yeah, let's say, okay, we are learning from you, Phil. Yeah, sure. Yeah, but first of all, here we didn't explore, you know, the effect of temperature. Sintering was done at a pretty low temperature because you are not only with glass particles here, but you also have PTFE, which is a polymer. So you cannot, you know, go beyond, let's say, 180 or 200 degrees centigrade, you know, because you'll start degrading the polymer. So working at these low temperatures, you know, it takes some time, you know, to sinter. But roughly speaking, you know, sintering never happens, you know, when you go to melting temperature. So sintering is always, you know, relatively low temperature compared to the melting temperature. And then the extent of sintering and the mechanical properties would strongly depend on the sintering time. So everything is controlled by the duration of sintering. And yes, there you have degrees of freedom even at low sintering temperature.
Thank you, sir.
By the way, in this case, may I already, it's time over?
Well, please to the time limit, maybe
all right, okay.
You can discuss through the email.
Thank you.
Professor Yarin.
Thank you for having me.
So move on to our next speaker. Our speaker is from could you
I'm here.
Screen?
I can't share my screen.
Some harvesting system tribal case. Yes, I can.
Nice chair. Hello, everyone. My name is Yoon, and I'm working in a Rogers Research University. It's a great pleasure to make a decision in front of materials for young by society. And for Professor Kim and Professor Sang-gu Kim and Professor Joo-hoon Kim to let me in this kind of wonderful conference. So I hope everybody keeps safe in this difficult season. So considering limited time assigned me, let me quickly go through my presentation today. I will talk about, as mentioned by Chair, I'll talk about ultrasound energy harvesting technology based on tribal electrification. So I'm going to start to address what is the background behind this technology, and the second part would be working principle, but I don't really spend not so much time though, since many of you would be familiar with what is a tribal electric effect. So main part would be the result, how it performs, and our insights on our project. So some of you maybe heard about implantable medical devices, including a pacemaker. Those are mainly powered by primary battery, and so we should consider just imagine a number of surgery, taking devices out and implanting again new charged one to operate sustainably. So here it sounds pretty painful in cost. So there have been lots of efforts to develop alternative way to power those devices by using mechanical energy, for example. If you see on the right, on the top, you can imagine some kind of movement in the body for example, by organs could generate electricity by taking advantage of piezoelectric nanogenerator. Another approach that has been suggested is a wireless charging system based on electromagnetic induction and resonance. However, we might face with challenges considering their drawbacks. Number one, not enough power density of given device. And the second, electromagnetic field would be sort of invasive to the certain level to human. There's a very limited range of resonance frequency of the given technology. So we try to think about an idea to transmit relatively high power density sources. I mean, in a non-invasive manner. That's ultrasound. So ultrasound is, everybody knows what's ultrasound. It's sound waves with high frequency beyond 20 kilohertz, and especially transmittable through tissue, for example. So if we figure out the design that is capable of contact and separation between two layers that is electrically charged by tribal electrification, so it will be feasible to give it a try. So the key among the TNG research is that any materials could be developed as a TNG. So we have a flexibility in terms of design. So that's the advantage of tribal electric nanogenerator. So let me jump up to the computational study. So now we just went through a computational study to see how much level of pressure and thereby deformation takes place under ultrasonic environment. So we found that the layer structure, including the polymer and the metal electrode with a higher acoustic impedance, there's a chance to increase the acoustic pressure between the polymer and the metal. So which will cause this level of deformation through the polymer, like a 200 micrometer deformation, which is not really significant, but it's pretty much feasible to, if we design our device like a less than that value. So based on this calculation, we designed our device having lower than 200 micrometer the displacement. The photo presented that the polymer film that is the film that is a highly charged one by trilocation, which is like under the electrode with a certain distance, which is lower than 200 micrometer. So it is pretty straightforward to fabricate our device. So we just assemble that triboelectric material nicely onto the metal electrode and encapsulate the sidewall to hold their displacement. Just imagine if we keep applying the ultrasound to the device, there will be constant oscillation, which might cause some device to fail. So to avoid that issue, we just encapsulate the sidewalls to make the device to work sustainably. So this slide shows that the final device design consists of not only power harvesting part, but also we can see there's the charging part, because at the beginning I mentioned this is developed to power the medical implant for a period of time. So to characterize our device performance, we arrange our experiment shown on the right side. So at the beginning, we tested our device in a water environment because ultrasonic attenuation is close to zero in water. So we could transmit ultrasound as much as we can. So we use ultrasound at 20 kilohertz, which is an inaudible sound. And generally, in a triboelectric nanogenerator research field, we measure the electrical output voltage and the current. So about the 10 volt of voltage and 427 microampere of the RMS current were detected, measured with a 3.7 by 3.7 centimeter square dimension of device. We choose that dimension because in 2019, when our paper published, the size of the pacemaker, for example, it's within that the size 3.7 by 3.7, which is pretty much fit on the size of the pacemaker. So with this device, we also calculate power level in optimum impedance. It reaches up to 7 milliwatt when 3 watt per centimeter square of ultrasound enters through the device. So, and as mentioned, we also tested our device to see if it is feasible to charge the storage. And other than capacitor, we successfully charged a rechargeable lithium-ion battery within 4 hours, which is pretty outstanding work, I guess. And since our device is aiming to power something implanted inside the body, so which will be pretty much associated with implantation depths, which is we should associate with the working distance from the ultrasound probe. So considering the ultrasound source itself, our 20 kilohertz has a maximum pressure level at 4 to 5 millimeter from the ultrasound probe. So that is also verified through not only experiments. You see the output performance goes maximum at that range 4 to 5 because there's a maximum pressure level which will highly oscillate the polymer fillet. But also we also check with the computation study, which is pretty much agree with our experimental result. The center result shows that the displacement at 5 millimeter shows the highest displacement level, which is originated from the maximum pressure level. So other than water environment, we also tested our device in various circumstances in terms of medium. So that has a varying ultrasound attenuation coefficient, I can say. So we experimentally found that we could harvest ultrasound even under the bovine serum and the rats, and even under porcine, and especially I can say the porcine skin that has a pretty much similar ultrasonic attenuation property with the human ones. So, which is pretty promising in terms of energy harvesting technology. So here's a summary. So in 2019, when it published, this project is first time to suggest ultrasound-driven travel education to power medical implants. And on top of that, there were no report to directly charge rechargeable lithium-ion battery driven by triboelectric nanogenerator. I'm very glad to achieve this with Professor Sang-Woo Kim. And I'm always thankful for my academic supervisor, Professor Sang-Woo Kim. And after I got my PhD in 2018, I started my career last year in 2020 in Professor Rogers' group. It is outstanding experience here with many postdoc and graduate students from countries. Thank you, and you may ask any question, then I'm more than happy to answer it.
Okay, thank you for a very nice talk, Dr. Yoon. We have 1 minute for the Q&A session, so maybe we can have one quick question for the presentation. Is there any question from audience? Probably the connection is not very stable. So actually, I have a quick question.
Okay.
So you transmit the power through the ultrasound. I mean, through the body. Is there
Yes,
any
that is-
impact to the body cells by the ultrasound?
That's really good question. Thank you for asking, Professor Lee. Well, yes. That's why at the very beginning we found some regulatory the standard. When we use ultrasound, there's a certain level of power we could take advantage for the medical purpose, which is 1 watt per centimeter square of ultrasound. That's the level of ultrasound we use to avoid any possible the hazardous phenomena through the tissues. Yes, definitely, that's a pretty much important aspect to consider when you use this ultrasound.
Okay, thank you for very nice talk again, Dr. Yoon.
Thank you.
So let's move on to our next speaker, Professor Deep Jariballa. Professor Deep Jariballa, are you there?
Yes, I'm here. Can you see my screen?
Yes, I can see your screen. So
Can you hear me okay?
yeah, it's good. Let me introduce you briefly.
Sure.
Professor Jariballa is an assistant professor in Department of Electrical and System Engineering at University of Pennsylvania. He completed his undergraduate